We will now move on to the topic of analysis of variance. I'm going to start with a motivating example. A topic of ongoing public interest is whether passive smoking, exposure among non-smokers to cigarette smoke in the atmosphere, has a measurable effect on pulmonary health. White and Frobe studied this question by measuring pulmonary function in several ways in the following 6 groups. And this was a study that was done in the New England Journal of Medicine in 1980. So the 6 groups are non-smokers, people who themselves do not smoke and were not exposed to cigarette smoke at home or on the job. Passive smokers, people who themselves did not smoke and were not exposed to cigarette smoke in the home, but were employed for 20 or more years in an enclosed working area that routinely contained tobacco smoke. That's right, people. People used to have to go to work, and then there would be people smoking in the office, and they would have to be breathing cigarette smoke all the time while they were working. It's a different time now. Non-inhaling people are people who smoked pipes, cigars, or cigarettes, but who did not inhale. I think we have a former president in that group. That joke actually killed in the mid-1990s, but you'll probably have to Google it. Light smoking, people who smoked and inhaled 1 to 10 cigarettes per day for 20 or more years. That's right, 10 cigarettes a day is considered to be light smoking. Moderate smoking, people who smoked and inhaled 11 to 39 cigarettes per day for 20 or more years. See, 39 cigarettes, that's moderate smoking. Realize that's when people are smoking 2 packs of cigarettes a day, or just a little bit less than that. And then heavy smoking, people who smoked and inhaled 40 or more cigarettes per day for 20 or more years. Okay, White and Frobe assessed the pulmonary function by measuring what's called forced mid-expiratory flow, or FEF. They were interested in comparing the mean FEF among the 6 groups. So you'll notice there are 6 groups labeled 1 through 6, and the mean FEF for the non-smokers, who should be the most healthy, is 3.78, and the mean FEF for the heavy smokers, which should be the least healthy, is 2.59. And our goal is to use the technique of ANOVA, or analysis of variance, to analyze whether one variable is the same across multiple populations. In this case, the one variable that we're looking at is the mean FEF. Okay. Now, you might ask yourself, we have these 6 groups, why not just do repeated t-tests? Why not compare the means in groups of 2 using just unpaired t-tests? Well, the answer to that is, why don't we look at the probability of type 1 errors? So suppose that we fix the probability of a type 1 error at alpha being 0.05. We now want to compare 6 populations, and in order to do that and compare them in groups of 2, we would have to compare 6 choose 2 pairs, or in that case, 15 pairs. So first of all, we would have to do 15 different comparisons to look at each of the smoking groups in pairs. And then the probability of making at least one type 1 error is going to be, it's going to be the probability, 1 minus the probability of no type 1 errors, using that complement rules. And that's going to be 1 minus, let's see, if we're going to make no type 1 errors in 15 different comparisons, then that means that we're not going to make a type 1 error. That's the probability of 0.95. And then we're going to assume that all of these pairwise comparisons are independent, so we'll take that to the 15th power. Now, if we work that out, that ends up being 0.537. So this is saying that the probability of making at least one type 1 error amongst the 15 comparisons is going to be 53.7%. So we can't be looking at comparing means in groups of 2 using the t-test, okay, because the type 1 errors are going to continue to grow as we introduce more groups. Now, I did assume that the probabilities here were independent, okay, but they're actually not quite independent, okay? So if we were to compare 6 groups, then the probability of a type 1 error is not 53.7%, it's 37%. But that's still quite bad. It's nowhere close to the 5% that we were hoping for. So instead, we're going to turn to analysis of variance. So why will we consider this analysis of variance technique? Okay, so there's going to be some themes running through this lecture. Okay, so first of all, it's going to make simultaneous comparisons of multiple samples. So we're going to be able to kind of run all the comparisons at once, okay, and get that error down to, probability of a type 1 error down to 0.05. And it's going to compare the variability both within and between the samples. So we're going to talk about that in a little bit. But essentially, we imagine that smoking has a different effect on different people. So the people who are heavy smokers, there should be some variability in their pulmonary health. And the people who are light smokers, there should be some variability in their pulmonary health. Okay, those variabilities within each group, okay, are going to be how different people react to, say, the cigarette smoke or how much cigarette smoke they're getting. Okay, but there's also going to be variability between the samples. Okay, we expect that people who don't smoke will have better health than people who smoke more than 40 cigarettes a day. So there should be some variability between samples. And ANOVA can be extended to study the effects of multiple experimental factors. So what's nice about the ANOVA technique is that we can actually extend what I'm going to show you today in this lecture to having multiple variables. Maybe we'll have pulmonary health plus some sort of measurement of heart disease. Okay, and we can look at both of those factors amongst the 6 groups. Okay, so in order to study the analysis of variance technique, I'm going to have to introduce some terminology. Okay, the first thing is that mu is going to be the underlying mean of all groups taken together. So imagine we take all the people and we measure their forced mid-expiratory flow, their FEF, and we get a mean for everyone. What is the mean for the general population? Then mu sub I will be the underlying mean for each group I. So we would imagine that there could be different means for people who don't smoke, and then people who have light smoking and people who have heavy smoking. And so we're going to have an underlying mean for each one of the groups. Now, y sub ij, that's going to be the value of the jth observation in the ith group. So we have 6 groups, okay? So you can imagine that y sub, let's say, 8, 6, okay? That's going to be the 8th observation in group 6. And group 6, I think, was the heavy smokers. Now, y sub I bar, that's going to be the sample mean. So y sub I bar is going to be an estimator for mu sub I. And then y bar, also sometimes called mu hat, is the grand mean, okay? And that estimates mu. So y bar is going to be our estimate of mu. Tau sub I, that's mu sub I minus mu. That's the difference between the mean of the ith group and the overall mean. And then tau sub I hat is going to be the estimator for tau sub I. So that gives us an idea of how one mean, say, deviates from the overall mean. Epsilon sub ij, that's going to be y sub ij minus y sub I bar. That's an error for an individual observation in J in the ith group. So that's how far one individual observation deviates from the mean of their own group. Okay, and so what's nice is that we can write y sub ij. We can think about one observation as being the mean for that group plus how much that person deviates from the mean within that group. And then y sub ij minus y bar, that's going to be the deviation of a data point from the overall mean. So one thing that's nice is we can write this y sub ij minus y bar if we subtract y sub I bar and then we add y sub I bar back, right? Because the two of those would cancel to 0. Then we can think about y sub ij minus y bar as being composed of two pieces, okay? So that's going to be e sub ij, that's the deviation of an individual from their own group, and tau sub ij, that's the deviation of one group from the overall mean. Another way that we can look at this is that we can write y sub ij as being the grand mean plus the group effect, okay, which is how far one group deviates from the overall mean, plus the random error, how far one individual deviates from the rest of their own group. Okay, so y sub ij is one observation you can think about as being the overall mean plus the variation between groups plus the variation within groups. Okay, now that we have that terminology, let's talk about what hypotheses we're going to test with this analysis of variance. So our null hypothesis in this case is we have, say, 6 groups, if we're using the smoking example. And our null hypothesis is that nothing interesting happens, that smoking has no effect on pulmonary health. So we're going to look at mu sub 1 is going to equal mu sub 2 is going to equal, all the means are going to be equal. That's the simplest explanation in which nothing interesting happens. Another way to write that is to say that tau sub 1 equals tau sub 2 equals all the way down to tau sub 6. They're all equal to 0. Okay, remember the taus are how far a group mean deviates from the overall mean. Now we want to look at the alternative hypothesis, okay? And there are lots of different possible alternatives, but I want to choose the one that directly contradicts H0. So in this case, that's going to be that at least one mu sub I is different from the others. So the conclusion that we get if we're able to reject the null hypothesis with ANOVA is at least one of the means is different from the others. What's important here to understand is that we will be able to say one of the means is different from the others, but we won't be able to say which one. Okay, so we're going to have to do further testing to figure out which one is different from the others. But first we just need to know, is there a difference between any of the means? Okay. And so the main idea here with ANOVA is going to be we want to find evidence of the difference in the mu sub i's. And the way that we're going to do that is we're going to look at two factors, the within group variability and the between group variability. Okay, so I want to show you a couple pictures. Okay, so the first picture that I'm going to show you has some data points for 6 different groups. Okay, and each one of those groups has their own group mean. So we have like y sub 1 bar maybe is there. So y sub 1 bar is there. Okay, we have maybe a y sub 2 bar, a y sub 3 bar, y sub 4 bar. So we have a mean for each one of the groups. And you'll notice that there's variability for each one of the groups. So we said before, we expect that pulmonary function should vary between individuals despite whether or not they're smoking. And so you see variability within the 6 groups. Okay, and so A, as you see marked here, that's supposed to measure the within group variability. That's the y sub ij, those are observations in group I minus y sub I bar. So that's how far they are from the group mean. Okay, so that's the within group variability. And then there's also, if you notice, there's variability between the groups. Okay, how far is each mean from the overall mean? And I got this from a different book which uses 2 bars for the overall mean, but we'll just use 1. Okay, so y bar for the overall mean there. And you can see that the variability between the groups, B, is large compared to A. So because there's more variability between each of these groups than within the groups are clearly distinguished. Okay, because those groups are clearly distinguished, we believe that the means are probably different. Okay, so here I'm going to say that the groups are clearly distinguished. Let's compare that to a different sample. Here again, we have 6 different groups, and you can see that we've kind of labeled where the group means are in this case. And you'll notice that the group means are all pretty close to each other. Okay, so that means the between group variability is small. Okay, so remember B here is between group variability. Okay, but within each group, and you're looking at these 6 different groups, there's a lot of variability amongst the individuals. Okay, we've got a variability from here to here in the first group, and here to here in the second group. And so you see A there is a measure of the within group variability, and that seems to be quite large compared to the between group variability. So here it's hard to say that there's actually a difference between the different groups. Okay, so we do get different sample means for the different groups, but there's not really a distinguished difference between the groups. So B is small relative to A. Okay, and therefore we are unable to distinguish the groups. And it's this idea that we're going to build upon for analysis of variance. Okay, the punchline is that the variation between group means must be large relative to the variability of the data points within groups to reject the null hypothesis and conclude the group means are different. So if our picture looks like this, where we can distinguish the groups, then we will reject the null hypothesis. If our picture looks like this, where we're unable to distinguish the groups, then we will fail to reject the null hypothesis. And hopefully these pictures give you an idea of how the ANOVA test is going to work before we get into the details.